Hello and welcome everyone to this past marathon, Modernizing Your Data Platform. We're excited you could join us today for Pedro Lopes' session, Intelligent Query Processing in SQL Server 2019. This past marathon features back-to-back live webinars delivered by expert speakers from the past community. The sessions will be recorded and posted online after the event. You will receive an email letting you know when the recordings are available. My name is Ree Irish, your moderator today. I'm pretty involved in PASS. I run the Women in Technology virtual groups. I help run SQL Saturday Atlanta, and I help run the Atlanta user group. I have a few introductory slides before I hand the reins over to Pedro today. If you require technical assistance, please type your request into the question pane located on the right side of your screen, and someone will assist you. This question pane is also where you may ask any questions throughout the presentation. Feel free to enter your questions at any time, and once we get to the Q&A portion of the session, I or Joe Sack will read your questions aloud to Pedro. You are able to zoom in on the presentation content by using the Zoom button located on the top of the presentation window. Please note that there will be a short evaluation at the end of the session, which will pop up after the webinar ends in your web browser. Your feedback is really important to us for future events, so please take a moment to complete this. In the lead up to SQL Server 2008 end of support, we've recruited Sandy, an expert in all things migration, along with an all-star lineup of speakers from Microsoft and Intel, to smoothly guide you to your final destination, a modern data platform. Whether you're interested in moving to an updated on-premises cloud or hybrid solution, PASS, Microsoft, Intel, and Sandy, of course, have teamed up for a must-attend series of webinars, in-person events, and migration resources dedicated to giving you the tools you need to migrate with confidence. Visit pass.org/modernization to see the collection of on-demand videos, helpful blogs, presentation slides, and other industry-leading learning content from PASS, Microsoft, and Intel. This past marathon session is presented by Pedro Lopes. Pedro is a senior project manager in the database systems group with focus on SQL Server's relational engine and programmability space. He has an extensive background in performance tuning and optimization, and also connects closely with several high-profile SQL Server customers and partners in the field to understand more about product usage and gather feedback that drives improvements into the product. And without further ado, here is Pedro with Intelligent Query Processing in SQL Server 2019.
Thank you, Ree. And I'm also joined by Joe Sack. He's doing the heavy lift of answering questions that, in case we have too many to actually speak during the session. I'm just wanted to say hi in person, but I'll disconnect my webcam now because I'm not big on webcasting my face. So without further ado, this is our agenda for today. It's quite ambitious to cover all this in approximately 57 minutes, which is what we have today. But it's all about the road to an intelligent database that we've set ourselves a couple of years ago, or a little bit more than that, in what is a common database engine across Azure SQL Database and SQL Server. We started to track that path back in SQL 2017 with something we called the adaptive query processing back then. We've actually enlarged the scope and we're calling it intelligent query processing going forward. And you'll see kind of a drill down of what we have done in this space so far, and there's much more to come. So without further ado, let's talk about intelligent query processing, as we've introduced in the last few versions of SQL Server, but obviously also Azure SQL Database. Again, same database engine, exactly same that runs on both platforms. So this is a rather complex tree, but just to give you a sense of how intelligent query processing has been evolving over time. And what we do with intelligent query processing is that we want critical parallel workloads to improve when they're running at scale, because we have a constantly changing world of data, and data distributions change. Data that exists in the tables change constantly, so we need to keep up with a notion of predictable performance and that's where intelligent query processing comes in. So these family of features are available by default on the latest compat level settings, depending on whether you're running in 17 or already in 19. So the ones you see in blue on the screen will be available in SQL Server 2017 if you are running DB compat 140. The ones that you see in grayish will be available in SQL Server 2019 and obviously Azure SQL Database if you're running DB compat 150. The only, and there's an asterisk there, the only exception to the DB compat gate will be approximate query processing because that's not gated by DB compat itself. And we'll talk a little bit more about this. So the point with intelligent query processing is that we want to address critical and somewhat historical issues with that some workloads face when running in our database engine, and do so delivering those benefits with minimal implementation effort. In most cases, with zero implementation effort. It just works. A code that ran the previous database engine or a previous DB compat, when moved to the DB compats you see on the screen, and it's eligible for those features to work, it just does. And we'll see, time permits, a few demos. If we don't have time to run all the demos I would want to, I will leave you absolutely with a link that you can go run the queries, the demos for yourselves. Those are all on our Microsoft GitHub, and please feel free to run them, and any questions come back to us. So we'll start with one classical problem space, which is the existence of multi-statement table-valued functions in our code. Now, for many, many years, if you've been working with SQL Server, there was, once upon a time, we actually evangelized the use of table-valued functions, namely multi-statement table-valued functions, as they came around in SQL 2005, if my memory serves me correctly. Like any user-defined function, in this case TVFs, they're very useful because you can write the code once to, in this case, to maybe have logic inside. And as a developer, you write that once and then you use it across your code. However, multi-statement table-valued functions are, for all intents and purposes, objects that only exist at runtime. So therefore, they're not actually physical tables, although they actually read from physical tables, right? So they're treated as a black box by the query processor. And because we don't hold statistics, we don't know how many rows may exist in that multi-statement TVF until runtime, we use a fixed optimization guess. As you see in the right portion of the slide here, before SQL 2017, actually to be more precise, up to database compat level 130, as you see in the top corner, we always guessed that 100 rows would flow from a MS TVF. Now, if you have just a few rows, maybe even a little more than 100, 200 would be fine, perhaps, and that doesn't really have for the most part, doesn't have a significant impact on how we optimize with MS TVF in the mix. The point is, when you start growing the number of rows you have in those objects to a few hundreds or even thousands, then all bets are off. Because for the most part, you will see that the query execution plan that we come up with is inefficient. So that introduces, obviously, performance issues. Now, interleaved execution is that was introduced in SQL 2017 specifically for the 140 compat mode, as you see also in the top right corner there. What we'll do is, the first time a query comes in that references an MS TVF, we will materialize that MS TVF for the first time, and then use that number of rows from that materialized TVF, MS TVF, to continue with the optimization with that number of rows in mind and carry on execution. And for the most part, we do see that we get good plans. So in essence, unlike the previous DB compat level, we start optimizing a query. As soon as we hit the MS TVF, we'll execute it. So it's very important to know that the first execution of the TVF will define how the plan is optimized. In this case, let's say 500,000 rows actually are coming from that first materialization. And obviously, being an MS TVF, it may depend on the incoming parameters. The point is, we'll optimize with that number in mind. That's assumed for the first execution. The plan is cached, so therefore any subsequent execution will leverage that optimized plan. So any downstream operation that exists in the query plan that uses that data from the MS TVF is therefore also leveraging corrected cardinality estimations. So that really drives a needle and improves performance of SQL statements that make use of MS TVFs. Now, the other classic problem that we addressed back in SQL Server 2017, and therefore it's available in 140 compat mode, is the old issue of finding spills in our executions, or to put it more broadly, any kind of misused memory. So if we're not able to properly estimate the amount of memory that a certain query will take to execute, then one of two things will happen. One is if we have misestimations, so we're estimating less memory than actually takes to run a query, then that results in spills. And probably most of you in your professional lives have seen spills to TempDB, either by a hash match operation or a hash aggregate or even a sort. That just means that the estimation of the initial estimation for the amount of memory the query would need was incorrect, and therefore we needed to go and resort to TempDB, which introduces I/O and therefore is slower. If we overestimate memory, that's also an issue, because think of a case where you have, just to make math very simple, you have a 10 gigabyte RAM SQL Server, and you're running a number of queries, and we estimate that 1 gig will be needed to run a specific set of queries, right? So at most, you'll be able to run 10 of these queries at the same time, given that you only have 10 gigs of RAM. But let's say that those queries that we estimated would need 1 gigabyte, and we actually provided 1 gigabyte for the query to execute. In the end, they actually only needed something like 100 megabytes. Now, this is a severe overestimation of memory, and it may stem from a number of reasons that we actually don't have time to cover today. Maybe lack of proper statistics, it may be a number of other issues. The point is, excuse me, if we have this situation, we are binding our resource, the resources of our SQL Server, and we're hurting the ability of running more concurrent workload. Now, if we were able to actually correct the memory that we actually use, so the estimated memory can be, in this case, lowered down to a closer amount of memory that we actually need to run the query, then suddenly, instead of running 10 queries at the same time, you can run 100 queries at the same time. So it's just increases concurrency. Now, in SQL Server 2017, we introduced a memory grant feedback mechanism for batch mode queries. That means that when you're executing a query that runs in batch mode, so back in 2017, this means that you need to run a query that makes use of a column store index in order to trigger batch mode. We'll adjust the memory grants based on the execution feedback. So for example, take the first execution, and it's the example where we have a spill because we estimated the query would need 10 megabytes, and it actually ended up needing 100 megabytes. So as the first execution will obviously have a spill there, but we will learn from that spill, and in subsequent executions, we'll keep adjusting the memory grant that's needed to be closest to the actual memory that is needed, because we aim to run that operation only in memory without resorting to I/O, and up until a point where we find that we found a stable point where we're actually only taking the memory we need, and at that point, the query runs without spills. Now, if we find the query is actually, it oscillates a lot, let's say you have a parameter sensitivity issue that kind of drives up and down the number of rows coming out of your query, then that we see too much oscillation, and we kind of may disable the memory grant feedback mechanism, in which case you have other means of doing this in a non-automated fashion, like, for example, using the max grant percent hint. So the bottom line is that memory grant feedback will remove spills if they're happening, or improve concurrency only for repeating queries. So this is not a means to handle parameter sensitivity queries. Just wanted to put that out there. Now, back in 17, we also introduced batch mode adaptive joins. So adaptive joins that, as the name indicates, only run when the query is executing in batch mode. Now, what happens here is during execution of an adaptive join, which is actually a physical operator in a query plan, if you ever saw one, we will defer the choice of the actual join, physical join type, hash match or nested loop, to later in the execution as the rows are traversing and incoming into the query plan. So what happens a lot of times is if cardinality estimations are skewed, meaning they are incorrect, and this means that the number of estimated rows is very different from the number of actual rows coming in. In this case, it could be like an index seek or an index scan. Then what may happen is, because we have these skews, we would end up in previous versions choosing an inappropriate join method. Like we would choose a hash match when probably a nested loop would be better, or vice versa. Because that all has to do with the number of rows that flows through the join. A nested loop is usually or typically better suited for small inputs and less number of rows flowing through the join. Typically, when you have properly indexed inputs. A hash match is actually much better for larger inputs, and even those that are not properly optimized from an indexing perspective. So what adaptive join will do is we'll have something called an adaptive buffer, which is basically building, getting the rows as they come in from the build input. And we have an adaptive threshold. In case we cross that adaptive threshold in terms of number of rows, then we understand, oh, actually this was poorly estimated and probably will need to run through a hash match because we crossed the build threshold. Oh, if we don't cross the adaptive threshold, then we can carry on with the nested loops. This means that we defer to execution time the actual join type that we're running with, which means that if queries can drive a widely variant number of rows that would benefit from one join implementation or the other, this actually takes care of it in runtime. So it's actually very cool from that perspective. Now, in SQL Server 2019 and Azure SQL Database, with 150 compet level, we also introduced memory grant feedback now for row mode. And you may have seen blog posts of actually trying to kind of hack the memory grant feedback mechanism by introducing a null-based column store index to trigger batch mode, because obviously people wanted to take advantage of the memory grant feedback mechanism, which makes total sense. So what we've done is we've opened up the memory grant feedback mechanism to also work in row mode, which means that now every single query that you run in your SQL Server can leverage memory grant feedback mechanism. So therefore, if it spills to disk, we'll correct that misestimation. If we actually are taking too much memory, so an excessive memory grant, we'll correct that wasted memory and will improve concurrency going forward. So it's exactly the same problem space that we've discussed a few minutes ago with batch mode memory grant feedback, now applying to row mode. And in case you want to understand, by the way, this is also applicable to batch mode memory grant feedback. If you look at an actual execution plan and you want to understand if and how is memory grant feedback helping you, you'll see that there are query execution plan attributes to let you understand where we sit in terms of the adjustments being done by the memory grant feedback mechanism. You see here highlighted in green a couple of properties. One, it says whether the memory grant feedback mechanism is enabled, and we see yes, and whether it's adjusting memory. And if you recall, actually it's just here, we can see one of three states. Actually, one of four states. We can see that yes, but it's first execution. This obviously you would see that state in the first execution of the query. Adjusting, it may reside here for some time as we keep looking and learning from previous executions in order to find a stable memory grant that this query needs. And after we find that, as you see in this case, we turn the state into stable. Now we also see here that the grant of memory, which is here, the memory grant, the memory that SQL Server provides this query to execute in the first place, and without this memory being available, the query doesn't execute at all, it needs to wait. And we see here that the last requested memory was this one, so we have that information also here. And as long as we keep inside this value, we have a stable memory grant that would again withhold the memory uses that we've seen in the previous execution. So it's rather useful to understand whether we are leveraging memory grant feedback. For row mode, again, this is only available in 150 compat mode. Okay. Now moving on to another problem space, table variables. Now this is also a very common development artifact that we find in code that's been there for many years. So especially if you're dealing with applications that were born in smaller systems for a smaller number of users perhaps, and therefore a table variable is good enough and fast enough for me to just dump some rows into an interim data set, and then I'll use for some other operation. And for a small number of rows, this actually works fine. So you see here the legacy behavior, or the behavior up to the 140 compat level, is that a statement that references a table variable, because the table variable, much like an MS-TVF, only exists at runtime, then we don't have statistics on it, like we would with a temporary table, right? Because it's a physical table that exists in TempTV. So much like MS-TVF and MS-TVF, we need to guess, we need to estimate the number of rows that will be held by a table variable. In this case, the compilation always assumes that one row exists in the table variable. But in the real world, we know that a lot of times more than one row exists in a table variable. But guess what? We use that fixed estimation to optimize a plan that then, when we find a lot more rows in these table variables, the plan is inefficient when it comes to runtime. So what we've done in 150 compat mode is that we will defer the compilation of a statement that actually has a table variable until the first execution of the statement. So very similar mechanism where when we're compiling the query, we find that a table variable exists in the code. So what we'll do there is we'll delay the first compilation of the statement that references one or even more than one table variable. And when we are actually going to execute that, we'll materialize that table variable and use that cardinality estimation to optimize the plan. And then the plan is obviously placed in cache, and subsequent executions can take advantage of that. Okay, and there's the questions so far. I know I'm kind of going in a fast pace, but we do have a lot to cover. Reed, do we have any questions so far?
We do, but Joe is on it.
Joe is awesome. I know. I mean, I love Joe. It's just awesome like that. Okay, let's carry on then.
Well, we do have one request, and I think you'll probably get to this in demos. It says, if time allows, please show an example of a batch mode adaptive join. So yes, you may or may not get to that, but I wanted to throw that out there.
If I can only do one demo, I will do that one. Absolutely. Good feedback. Okay, so another problem space we tackled is the use of user-defined functions, specifically scalar user-defined functions. Now, user-defined functions or scalar user-defined functions, they're implemented to return typically a single data value. Now, this is another elegant way of writing code once and reusing the code many times. So developers do like to use functions as expected. And a lot of computations, a lot of if clauses and business rules can actually be expressed in a UDF in an imperative form. So it's very easy to it's a very easy go-to object for developers. Now, the point is UDFs have a problem, and the problem with UDFs is that for every let's say I'm applying a UDF to a column in my select statement. The point is, for every single row that comes out of my select statement, I need to invoke that UDF for every qualifying row. Now think about a select segment that brings in 1 million rows, and for each row, for one or more columns, I'm invoking a UDF to do some calculations, for example. Now, that can become a problem, mainly because the query optimizer doesn't cost those scalar operators. We actually, they would be typically computing, so they're not factored in to the costing aspects of our query optimizer. So what may happen is something that seems very simple to implement. Maybe it's just finding an end of month date or something like that based on the incoming date time column. That when we invoke multiple times can actually bite us and decrease the performance of our query. So even the fact that we actually, for each statement that's compiled, we cache the plan. The point is we cache the plan with zero cost assumed for those scalar operators. So, and because, by the way, for every single run execution of that scalar operator, that function is executed in isolation. That means we cannot even optimize the internal code that resides inside that UDF. So it can be painful. That's the bottom line, and more so if you were expecting to have your query run in parallel. Because here's the thing, SQL Server does not allow parallelism to run for queries or to be used for queries that actually invoke scalar UDFs. So if you today have queries that are taking a really long time and you look at the execution plans and they are running in serial and you would say, oh, but this is actually the cost is huge. Why isn't SQL Server triggering parallel execution for this? There you have it, because it's a parallelism inhibitor to actually have scalar UDFs. Now, this is all up to 140 compat mode, because in 150 compat mode, we have the ability to inline scalar UDFs. Not all of them, but for the most part. And if you actually go, and the source for this is the white paper by MSR Freud, like this there in the bottom. And we do have the link in the notes once you get the slide deck later. What happens is when we are able to inline automatically the scalar UDF function, we are actually exposing to the optimizer the code that lies inside. So therefore, the optimizer will know that what's happening inside the UDF when it's compiling and optimizing a plan, and typically it will output a much more efficient plan than before 150 compat mode. Now, you could also achieve this manually, right? I've done dozens and dozens of performance enhancement exercises where part of it would be to take the code that resides inside the UDF, because it's a very useful programming object, but it's not very useful in terms of unleashing performance in database relational engines. So what we could do manually is crack open that UDF, whatever it's executing inside, if possible, inline it in your own code in case you're not running 150 compat mode, and you can achieve the same manually. Now, the beauty of 150 compat mode and this feature is that without any code changes, now you just exponentially increase the performance of queries that they may take advantage of scalar UDFs. So what we do is we will, as we encounter UDF is being called, we will parse that UDF. We will, as you see here, this is what being handled by it's being described in the Freud white paper. We will parse that UDF definition. We will combine those expressions that we find inside and pull them back into the original query. So we'll inline them in the query, if you will, as we optimize and build the plan. So, and this is done automatically. Not everything can be inlined. This is actually a screenshot from that white paper. There's a number of types of statements that can be actually turned into other types of algebraic expressions. For example, if I have a select from, that can be turned into a subquery. If I have a if clause inside my Scalar UDF, that can usually be turned into a select case expression, and so on and so forth. So automatically, when we find these sort of expressions, we will turn them into these expressions, inline them into the query that makes use of the T-SQL Scalar UDF, and optimize with that in mind. For all these cases, the output is you have a better suited execution plan, which is deemed efficient to run the query that you're trying to run. Now, are we on time right now? Are we good?
I think we're good. You're at the halfway mark.
Okay, good. So we'll actually probably have time for a few demos. That's good. Okay, so batch mode and column store. Now, why am I bringing this up? Historically, and if you recall a few minutes ago when I talked about the batch mode, memory grant feedback, and the fact that there was this sort of hack, quote unquote, to trigger batch mode by making our query leverage a null-based column store index, just to the fact to trigger batch mode, is because batch mode has been historically tied to column store. Now, column store indexes, as they were introduced back in SQL 2012, they were a way to optimize analytical queries that access massive amounts of data, but typically they need to get all the data that resides in few columns, not necessarily the entire record if we're looking at row mode, right? So a column store index can optimize the number of IOs we need to do to grab that massive amount of data, because they will only access the data in the columns that we actually need for our query. And because the data is compressed, it also achieves, we also enhance IO from that perspective. Now, when we introduce column store indexes, we also introduced batch mode. And that's because from a computing perspective, we understood back then that to read these massive amounts of data from single columns, it was inefficient to use the row mode CPU scheduling that we've been using, sorry, CPU processing that we've been using in previous versions of SQL Server. So as we introduced column store, we tied to it the batch mode execution. Now this allows query plans and the operators inside the query plan to process that data, that massive amount of data that's coming in a columnar format much more efficiently. And like I said a minute ago, it's built primarily for analytical workloads. Now these have come hand in hand back in SQL 2012, and this have remained hand in hand until very recently, because in SQL Server 2019 and Azure SQL Database, we've decoupled these two concepts. That means that we can now have batch mode not only on column store, but also on row store. And that's because sometimes you actually creating a column store index just isn't an option for you, right? So if you're not running a data warehouse, if you don't have even an operational data warehouse, if you have more OLTP type of workload rather than analytical, or let's say you are tied to the schema of the database that your ISV has set for your vendor database. So you're not actually able to go in and create the column store, although that could be feasible from a technical perspective. So depending on where you sit, the point is the column store is not always an option. But that doesn't mean that you wouldn't actually be able to leverage batch mode if it makes sense. That's where this decoupling makes sense, because now we can actually get smarter in processing analytical workloads and leveraging the CPU benefits of batch mode, even when we don't have column store indexes. So you have your traditional row store indexes in your table. Maybe it's your ISV database that's already properly indexed. But guess what? Just by moving to Azure SQL Database or SQL Server 2019 in 150 compat mode, you're able to automatically, for certain types of queries that are more analytical in nature, just unleash performance by automatically running those in batch mode. Now, We didn't introduce any new operator, by the way, so whatever, we just open up batch mode to be run for rowstore. So there's nothing, there's no new operator that you may find in an execution. Now here are the candidates, because not everything can or actually should run in batch mode, even on rowstore, because row mode on rowstore is still very useful for typically for OLTP workload, because it just runs more efficiently that way. However, if a significant part of the workload that you have is actually analytical queries, then batch mode becomes a win for your workload, and that's where we will enable it. So that's part of the and conditions for you to have to be able to run batch mode on rowstore. The other one is the workload needs to be typically CPU bound, meaning if creating a column store, like I said, is not feasible because you have a fixed schema in your application and you can support column store indexes, or you have, for example, you have triggers in your table and column store doesn't support triggers, so therefore you are unable to create a column store from that perspective, or even let's say you have the fact that creating a column store index itself would actually create a lot of overhead, because you have like an operational data warehouse where you actually read data from an analytical perspective and run some queries that are analytical in nature, but you have a OLTP kind of workload in terms of writing to your database. So actually the overhead of maintaining column store indexes would be too much. Then if you have these conditions, then actually batch mode on rowstore is for you, and that's where you'll see the benefits. Now, a few considerations here. There's no guarantee whatsoever that query plans will use batch mode. It depends on these conditions that I mentioned. So we'll actually be clever about it, and we'll only enable batch mode where we see the pattern that matches what we've covered in the previous slide. By the way, there's no guarantee that you will get a row mode plan if you were getting a row mode plan in a lower compat level. Once you move to 150 compat level, if the query is eligible to use batch mode on rowstore and it works better that way, that's what we'll use. So we're not guaranteeing that a previous row mode plan will remain row mode plan. Actually, that would be counterintuitive, right? And conversely, by the way, there's no guarantee that if you get a batch mode plan and later you actually add a column store index, that you will get batch mode plan on the column store. Actually, on the column store you would, but that the plan overall would run as batch mode. You may actually introduce a plan that runs parts as batch mode, the column store parts, and actually has other parts that run in row mode. This is because it's an entirely different ballgame, right? Every time you introduce a change to the underlying schema or you change your query, obviously we'll recompile the query, we'll get a new plan, and the new plan may not necessarily be what you got before for what was in essence a previous reality, if you will. So yeah, and that kind of speaks to what I was saying right now. If you mix column store and row store indexes, there's changes in subtle ways there that may actually derive in you getting mixed mode plans. So just keep that in mind, that if you change something, the outcome as a new plan is not necessarily similar to what you had before. Now, another area that we are tackling in intelligent query processing in what relates to 150 compat mode, actually, sorry, to SQL Server 2019 and Azure SQL Database, is actually a new T-SQL notation. You see right there in the title, it's approx count distinct. Now, this is supposed to be for a scenario where you need to actually count a number of records in the table, and especially when we're talking about ginormous tables with millions or billions of rows, and you need to have that query run multiple times. Now, here's the caveat. You can obviously do a select count distinct from those big tables, but what happens is, besides the time it takes to run that, it has a very large memory footprint. As we estimate the amount of memory that takes for a query to run in its memory grant, based on the estimated number of rows that we are touching, that also has an impact, obviously, on the amount of memory that we take to execute even just that select count distinct. Now, using approximate count distinct actually lowers the significantly lowers the memory footprint to run a count distinct query, but it's not for every scenario. Here's a few scenarios where approximate count distinct is actually useful for. For example, you have a dashboard that has a trend analysis, and that's running against a big data set that has millions or billions of rows. Now, being a dashboard where you have a trend analysis, it may not matter that your select count distinct is precise to the specific unit, but you actually are okay, because it's a trend analysis, with a high probability and a low error rate of getting a number of rows that is very approximate to the real number, but it still has some skew there. What I mean is, this function will be useful for trend analysis when I need to run that select count distinct query a lot of times, and I'm okay with a high degree of confidence in getting that count that may not exactly match what we are returning. Now, so for example, this is not useful for a bank. I wouldn't want my bank to use approximate count distinct when they are coming up with my bank statement, obviously. But so that's not necessarily the scenario. But for example, for data science, where you are exploring big data sets and you need to understand patterns in the data distributions quickly, exact values are usually not that important, but rather the trends that we're finding. So approximate count distinct is able to come up with a count distinct of a number of rows with a 97% probability, and it guarantees up to a 2% error rate. So it's very useful in these scenarios. And like I said a minute ago, not for banking applications or any scenario where an exact value is required. For example, if there's a workflow in an application that requires an exact count to then trigger some business process that will transfer money to someone or buy stocks in the stock market or something like that, then this is not for you. Okay, so just keep that in mind. I don't know how we're on time. Can someone read? How are you on time in terms of being able to?
You have 17 minutes to go.
Oh, awesome! So I'll be able to run most of them. Okay. So let me change gears here and open up my test server. Are we on questions? Joe, I see you've been very, very busy.
Yeah, so we're good on questions. There was one that was just general about new CE and old compat, and I'm thinking maybe for the scope of this talk, we can follow up with that question afterwards.
Okay.
Thanks.
Okay, so all these demos, by the way, you'll be able to find them in, let me actually, since we have time, I'll actually put it up here because it's just easier to get there. If you go to https aka.ms/IQP demos, you'll get to our GitHub repository where you see all the demos that I'll probably not run all of them today, but you'll see a lot of the demos that are available for all the features that we've discussed. All of them are based in the public sample of the worldwide importers DW database. So all the instructions are here. You can download the database. You actually need to enlarge the database using this script here. But then you see all the scenarios that we discussed. You have demos that you can run and explore by yourself. Okay. Just wanted to put that out there. Okay, so the first one, actually there was a request here to show batch mode adaptive join. So batch mode adaptive join is available in 140 compat mode. So let's use the database and set it to 140 compat mode. And to actually see it running, I'm going to enable live query statistics. And that's a feature you have available in SSMS. So in case you haven't seen it before, you just enable this button here, and you can see the live execution plan as it progresses. So let's run this query here. and we see the live execution plan. Actually, it's already done. We see the adaptive join here. Actually, let me do this. There we go. We see the adaptive join is an actual physical operator in the plan. And we see, so the physical operation is adaptive join. The logical operation that we're running is an inner join as expressed by the query. And the actual join type that was used in the end for this execution was a hash match, which actually it was also the estimated join type that we would be running. Now, look here, the adaptive threshold rows. So that means that for this query specifically, if the output of the inputs was over 68 rows, then we would move from running a nested loops to a hash match, and that was the case here, because we actually had 206 rows, which obviously is above 68, which means that after we found that we crossed that threshold, we no longer carried on executing or proposing the execution of a nested loop, and instead we went with a hash match. Now, looking at the query plan itself here, see how the input for the adaptive join was primarily this. Let me see if I can. Nope, that's not this one. So it was this column store index scan. So we started bringing in the rows from this cluster column store index scan. Once we crossed the threshold, then the inner table or the probe table for the join became one of these two operations, right? So you see here that it was this one. Oh, sorry, wrong. There we go. Was this clustered index scan, and we read 670 rows out of it. And the other operator, this clustered index seek, which would be used for the nested loops, had we gone with the nested loop, has 0 rows out of it. So we actually are able to see what the adaptive join operator did just by looking at a plan. We see how many rows it processed. We know what is a threshold for that adaptive join specifically, and we see what operations would be the other input for this join, and we see which one we actually use, because the one that will remain unused now shows a 0 number of actual rows. So we're able to actually see this in action, right? Now, what happens if I insert a row that doesn't exist in the table yet? Let me just do this and insert this here. Okay. Right. Okay, now let's run this the same query again, but now instead of a where clause where the quantity equals 360, we're actually looking for a quantity that wasn't in the index before, right? In the table before. So when you do this, we see that the actual operation actually flipped. Let me select this here. So we see that for this new query, the adaptive threshold rows were 9.8, and the estimated join type was a nested loops. And we see here that actually, oops, let me go further down. I forgot to bring the actual plan, which is something I should have done. Let me run this again. Yes, there we go. So we see the actual join type was a nested loops, and the estimated was also a nested loops. This is the adaptive threshold, and the number of rows that we actually got were 5. So because it is less than the adaptive threshold, we kept on using a nested loops rather than crossing over to an hash join. And that again is visible in the plan itself. We see the input as this column store index scan, and we see that the other input for the join is now this clustered index seek, rather than as in the previous plan, the clustered index scan, because now we use the nested loops, right? So you're able to determine what happened in terms of adaptive join behavior in the looking at the plan itself. But as you see, the plan shape didn't change. We still have an adaptive join. We have the column store index scan as the first input, and we have either a cluster index scan or a cluster index seek available to service either if we're going with a hash join or if we're going with the nested loops. And they're both present in the plan. We just on the fly flip between one and the other depending on whether we cross a threshold or not. And as we've seen, the threshold is adaptive and dynamic depending on the in this case the where clause that we run. Okay, so this is about adaptive joins. Now the beautiful thing is that these are batch mode adaptive joins. Now in SQL 2019 and in Azure SQL Database with 150 compat mode, we enabled batch mode to run on rowstore. Now, whereas this exact demo is running in 140 compat mode and it's making use of a column store, you now will have the ability to run adaptive joins without the presence of column stores, even when you only have rowstore indexes in your table. Again, if your query is eligible to use batch mode, right? Because batch mode now being available on rowstore, that means that everything that was available before just for batch mode, such as adaptive joins, is just unlocked and available for use. Is there a question? Okay, let's carry on then. We have 5 more minutes. I think I can run a couple more. So another one is the row mode memory grant feedback, right? And this works very similarly to batch mode memory grant feedback. So you see one, you'll see what you can expect from both of them. Now, using the same database, I'm going to set the database compat level to 150 because this feature for row mode is only available in 150 compat mode. For batch mode, it's available in 140 as well. So let's be on the right database, of course. I will, for the sake of this demo, I will simulate an out-of-date stats scenario. And now let's run this query. Let me actually bring up the actual execution plan, and let's explore what's happening inside. So this query is taking some time. This should take a minute or so, and I could have actually brought in the live execution stats. That's really useful to see what's happening as it is happening. Let's actually do that. I'll cancel. I'll bring in live execution statistics, and we'll see it as it is executing. So see here, the live plan. We're doing this table scan. We're from my order history table, and then we are joining with this index here, and we see that the hash match is now running 49,000 rows out of one estimated row, and you see there the huge skew in terms of percentage, right? That actually stems from this table scan. This table scan, SQL Server estimated that only one row would be coming out of the table scan, but actually 3.7 million rows came out of the table scan, which obviously then impacts the tree going up. And what we had potentially as a effective query plan, it's now inefficient. So if we move to the execution plan part, we see that obviously we have, as expected, a spill, and we see let me actually go back here. We see the spill wrote 52,000 pages to TempDB, which is quite a lot. And this query just was very, very slow. How can we see the numbers? By the way, we have newer properties such as query time stats. We see here that it took around 36 seconds to run this query here. In terms of memory information, let me do a live zoom here. In terms of memory information, here's what we get. Because we estimated such few rows coming out of one of the tables, the grant of memory was only 1 megabyte, right? But in the end, we needed more than that. In the end, we needed more than that for running this operation. So where is that? Let me go back here. Sorry, this needs to be run again. The procedure cache. Let's go back to running this. And there you go. So give it the same 30 seconds. I don't know if you've used live query stats before. This is really useful to see the query progress, especially for long-running queries or slow queries. And you actually have these numbers that will pinpoint you very explicitly where you may have estimation issues, such as this case, right? You can also see the time it took to execute each operation, right? So here, the larger amount of time is actually spent on the hash match as we are running this now, right? So it's done. Let's look at the actual plan. And let's look at the memory grant information. And we see that memory grant feedback adjusted. It says no, because this was the first execution, right? So we see that the 1 megabyte of granted memory, but you see the query actually used almost 2 gigs. So this is obviously very inefficient from that standpoint. However, memory grant feedback means that we'll learn from what's been happening. So if we run this query again, we'll start to see some things changing. Now, maybe not necessarily in the first subsequent execution, but we will start learning from the amount of memory that we've taken that actually in this case led to that spill. And as subsequent executions progress, we will see that we'll start adjusting that memory and bring it closer to the actual amount of memory that is needed, and therefore do away with the spills just automatically. Now, in this case, we're still very close to the 36 seconds, now down to 32. If we go to the execution plan, we still have the spill. And when you go to the memory grant section, we see that it's first execution. No, it's not. What's happening here? Why? Let's do this here. Okay. So now it was actually much faster. There's no spill anymore. Let's look at the memory grant information. We see that it's still adjusting, so it's still not finalized, it's still not stable, but it's already enough to remove the spill. We'll see the grant memory is now not 1 megabyte, but 625 megs. And it was enough in this case to do away with the spill, and that just happened automatically. So that's another way of, and this is not using a column store. Sorry about that. This is not using a column store, so it's all this query is running in row mode, which you can actually see up here. Actual execution mode for each of these operators, you'll see row. So you can also determine from there whether you're running operators in row mode or batch mode.
Pedro?
I think we're running out of time now, so let's go back to our deck. Like I said, all these demos are available online. You can run through all of them. So some of these features are still in preview, so we really need your feedback. If you see something that you don't think you should be seeing with the intelligent QP features, let us know. Please email us at intelligentqp@microsoft.com. All these demos that I've run are in this URL here, but you'll find other data-related demos in this other URL. There's a lot of this new features and tackling T-SQL anti-patterns that we have actually dealt with in the book that we just launched, Learn T-SQL Querying. So I would suggest you can, this is a shameless plug, yes, but I would suggest you at least check out the book here. And last but not least, we've created a number of shortcuts for some obscure parts of documentation with a lot of useful information. And this is just like one shortcut to rule them all. You have this shortcut here that if you remember this one, you can access all sorts of useful information in SQL Server documentation. So
Okay.
questions, they've been, yes.
We're at a hard stop. Joe has asked all the questions. I think the only one we had was that last features you show, is it turned on by default? I think
In the compat mode that we, as long as you use the compat modes that we show throughout the deck, as a minimum 140 or 150, yes, those are enabled by default.
Awesome. So thank you very, very much for speaking for us today. We really appreciate it. The next session is starting now. So those of you who are still in here and intend to see the next one, go ahead and end this one and head over. As we said at the beginning, the session has been recorded and you will receive an email with the link. And thank you very much for attending today. We really appreciate it. Pedro, thank you for speaking today. And Joe, thank you for handling the questions. Great job.
Thank you very much, everyone. Thanks all.
Bye.